Okay, just let me know when you want me to start. Okay, so in the second part of this session, I was asked to prepare some materials on the computational methods tied into software in order to do a demo of the packages that we've developed as part of the CM4 effort. I've never done one of these before, so we'll see how it goes. We had some trouble setting up the resolution of the screen. Hopefully that's our biggest glitch. Okay, so you've heard a lot, obviously, in the morning session about the theoretical background and motivation for these fluctuating hydrodynamic approaches, motivated in particular by looking at a wide class of problems at the mesoscopic level. So I thought I would, well, I guess I don't need to say much about the Landau-Lifshitz fluctuating hydrodynamics since we talked about that in the morning session. Just for completeness, I'll mention that the key thing that we're developing are ways of taking the Landau-Lifshitz fluctuating hydrodynamics and incorporating fluid structure interactions as a way of basically thermostating implicit solvent coarse grain models, polymeric fluids, things of that nature. So I said a lot about the fluctuating hydrodynamics approaches this morning, so I won't go into too much detail here, just to point out the two main regimes that I'll discuss today and that's currently available in our software release. So the first one is this inertial formulation of fluid structure interactions, where we're resolving two momentum equations, one for the hydrodynamics, and so that's given here, with the drag term coupling the fluid mechanics to the microstructure given here. And so the key is, in whatever particular model you're developing, is to make an appropriate choice of the coupling operators. Here, gamma being the velocity averaging operator that tells you the reference velocity with which to experience drag for your microstructure, and the force spreading operator that's given here. And we talked about the immersed boundary method, and we also talked about using adjoint conditions as a modeling approach to look at things like a colloid with translational and rotational diffusivity. This is how one thermostats the inertial formulation of our technique. And so the interesting point here is that you have the usual Landau-Lifshitz style fluctuating term, but in addition, because of the microstructure, there are these interesting cross correlations that arise from the drag term, which is coupling the microstructure degrees of freedom to the fluid mechanics. And then the microstructure equation has its own stochastic forcing term, which comes in here to model, again, those under-resolved collisions which are occurring with the microstructure through the solvent being replaced by that continuum stochastic field. Okay, and I've shown this earlier, basically the origins of Brownian motion being those the symmetry breaking in collisions on one side of this colloidal molecule and another, leading to Brownian motion. And we're replacing that with these stochastic random fields. And as I mentioned, there's a lot of utility to that in being able to filter, to be able to develop time-step integrators, exploiting things like a Fourier representation of the field. Okay, the other regime that we're also looking at is the overdamped regime. And in this case, this is, if you remember the perturbation analysis that I went through, this would be where you basically have eliminated all of those fast time scales, and now you're only retaining the dynamics of the microstructure. And so what's done here is there's an effective hydrodynamic coupling tensor that comes from the fluid solver. And there's a thermal drift term that's very important to incorporate, as I mentioned, in order to get the appropriate Gibbs-Boltzmann distribution with detailed balance. And then there's the thermal driving field, which is chosen to be 2 kBt, the hydrodynamic coupling tensor. So this would allow you to simulate, using our techniques, a similar regime as Brownian and Stokesian dynamics, but you could do this in principle without needing to know in advance the Green's function, which could be useful for complicated geometries and taking into account confinement effects. Okay, so that's an overview of the two particular cases that are currently available in the software. I'll mention that the software is integrated with LAMMPS. And so we had to come up with a name, so we call it Mango Selm. I'll tell you in a minute. The Mango part is referring to a graphical user interface that we've developed, and the Selm part obviously referring to these fluctuating hydrodynamic techniques. And so this is a custom package that you can integrate with LAMMPS. So you download LAMMPS, you download our package, compile, And if everything goes nicely, you won't get any compilation errors. If you do, there's a website that you can post your issues on, and we'll take care of those as resources allow. Okay, so the overall structure of our open source package is as follows. So I'm not sure how many people are familiar with LAMMPS, but LAMMPS is a pretty widely used now molecular dynamics package that's been developed at Sandia. I think Steve Plimpton was very early on in founding LAMMPS. I'm sure there are many others involved at this stage. And so the way that we're integrating with LAMMPS is we're allowing LAMMPS to take care of a lot of the microstructure modeling part of the problem, right? So if you noticed, you can have a general force law there. Well, I don't want to have to go back and try to do what Steve Plimpton's group can do at Sandia much better, which is things like particle mesh E-walls, right, which has been highly optimized in case-based methods. Looking at various types of clever algorithms for sorting particles to do pair interactions and things of that nature. So LAMMPS is mainly going to be handling our force laws, and the time-step integrators and all of that will be handled by my package. But there's a number of ways in which these things have to interface. And so just to give a little bit overview of the software layout, because this is helpful when you're trying to use these packages, is we have basically 3 different ways that you can interface with LAMMPS. You could write a raw LAMMPS script, which isn't so bad. LAMMPS has this scripting language which is pretty nice in terms of this language of computes and fixes. In that nomenclature, our method is a special type of fix. I'm not sure of the history of that term, but anyway. And we have 2 other ways now where you can interact with LAMMPS, which is often a lot easier as an entry point so that you don't have to generate all of these files and parameters in a self-consistent manner. One manner is to use a Python interface that we've developed and that sits on top of LAMMPS's Python interface. And basically what that does is generate XML files which control all of the different parts of a SELMS calculation, namely the setup of the Lagrangian degrees of freedom, the Eulerian mesh that you're going to use, the the fluid structure coupling operators, those lambda and gammas that I mentioned, and the time-step integrator. What we've done is, I think, a very easy entry point into using our techniques is we've developed in Java a graphical user interface which we call Mango, kind of the idea being that it makes things sweeter. So mango is a nice fruit, which I enjoy very much. And so when I was working on this, I decided to call the interface Mango. And what this allows you to do then is to set up models graphically, and basically by doing it through essentially like a spreadsheet type function plus a 3-dimensional geometric modeler, you basically can push a button and it'll generate all of the scripts and the XML files that you need. And really, I think the way to think about it is you might not do all of your modeling through the interface, but it's a good way of warming up and getting a sense of how all the different pieces behave, and at least it sets up for you a self-consistent model. Then the XML input is used then to drive the SELM package, and the SELM package that I mentioned has the various numerical integrators implemented. And then this outputs data from the simulations in a standard VDK formats, things like VTP and VTU formats for the flow field, or VDR formats for the flow field, depending on the particular solver. And also output, which is in an XML file, which you later can load up for post-processing. Okay, and LAMMPS also outputs some of the molecular dynamics formats like DCD files and so on, and you can utilize all of their functionality as well. But because LAMMPS knows nothing about our hydrodynamic fields, we have our own custom output, which is here. Okay, so that's the overall layout, and then within LAMMPS, again, our particular software package is this user SELM, which you can download and compile with LAMMPS. LAMMPS is handling for us the force interactions and the data output mainly, which is quite a non-trivial set of tasks and functionality in itself. Okay, and then SELM is handling the Eulerian mechanics, the fluid structure coupling, of course, the Lagrangian mechanics, and then if you have any kind of custom force law or interactions, maybe actively moving particles or something interesting and exotic, XML interface, and the data. Okay, so that's the basic outline of the software. And I'll just say a few things about the things that are available currently. I've said a lot about these 2 things. We've implemented a Lease-Edwards style method for imposing shear in the context of fluctuating hydrodynamics, and I'll get into a little bit, I'll show an example. This can be used related to the soft matter problems of doing essentially a little rheology experiment, so where you can shear the domain. That's fairly standard in molecular dynamics simulations, we've extended that into the context of hydrodynamics, which presents some interesting challenges, both in formulation and in coming up with good computational methods. I already mentioned that the codes have been developed to output standardized formats, so it's easy to do a lot of the post-processing of the simulations. Mango is a Java-based graphical user interface for setting up the models that I mentioned in a moment. It's good for generating scripts and data files, at least when you're getting comfortable with our sort of paradigm and our codes. Both of these have been set up in a way that's highly extensible, so that if you develop your own custom Lagrangian description, maybe you decide you want to model polymers using Chebyshev polynomials as opposed to point beat spring models, there's a sort of natural way in which your custom extensions could be easily incorporated into the software, both on the C or C++ codes through new objects, or in our interface by coding up a little version there. So this is just a quick sampling of the source codes. This is the C++ source codes, pretty large development effort at this stage. I mean, we're quite a few tens of thousands of lines of code. We've used this delegator design pattern to make it very extensible. So there's kind of a register of Eulerian types and then a delegator, which is parsing an XML file to figure out which one of the Eulerian types to use. You can easily code up your own. We've used here uniform periodic meshes, but you could even put finite element meshes and things like that as part of the SELM Eulerian. Lagrangian here, we're mainly using the LAMMPS atom angle style, although we will also allow some of the other types as well in the future. And then the integrators, there's a few different integrators available. Right now, I'm mainly going to focus on the quasi-steady state integrators. That's the easiest one to explain. And then the coupling operators I mentioned, we have codes to do the standard immersed boundary style coupling, but also this Faxon style as well. So this delegator design principle works very nicely because you can add an extra class, and most of the workflow is handled through a fairly standard interface, creating these new classes as needed. Okay, so there are really these four main classes corresponding conceptually to what you would do in one of these fluid structure interaction problems. We have classes for the Eulerian mechanics, Lagrangian mechanics, fluid structure coupling, and time-step integration. Those are the main four things. And you'll see there are corresponding patterns like this where there'll be XML files for each of these four things that you need in every simulation. So this pattern will repeat itself. Okay, and we've, as I mentioned, to make things standardized, I coded up my own custom XML parsers and so on. Okay, so the interface is graphical in nature, as I mentioned. You mainly will enter things through like a spreadsheet type of interface to set up parameters. I'll say a few words about the format in a moment. But anyway, it's a pretty big undertaking to come up with a usable graphical user interface. So this is just a sampling of the source codes. I have on the order of 50 to 100 classes. We wrote our own custom 3D rendering routines as well to kind of have everything tightly integrated. And so just to give an overview there, it's all done in Java, object-oriented based. Again, we've used this kind of delegator design pattern to allow easy extensibility. And in fact, we use dynamic object loading properties in Java. So even if the bytecodes have been compiled, you can put in your own class. You don't have to recompile the whole entire Java library. And it will, if you register it, will load into the interface. Again, you have these four main classes that mirror what's in the C and C++ codes, as I mentioned before. And again, it's very extensible. So if there are things that you have interest in working on or making it available to other people, I'd be very happy to talk with you about how to kind of click it into this larger framework. And so I'll also mention that we've also implemented these custom classes for rendering the models in 3D and allowing you to edit them geometrically. And I'll show you the utility of that in a little bit. So the interactive editor allows you to do things like viewing the model from different angles, obviously, adding and removing control points. You can add and remove bonds between points, so you can create custom topologies, or you can even add custom forces very particularly in the model. And we also have some codes as well for tracking physical units if that's of interest to you. Okay, now what I should also mention is you don't just have to point and click to control the interface. We also integrated things with what's known as Jython. So it's basically a version of Python, which has been implemented within the Java framework. And so you have most of the standard libraries that you would have in Python. And so what we've done is, if you look at the interface in the lower right corner, I implemented in Java an interactive editor that makes calls into the Jython package. And so This allows you to do things like pickle data. You can have scripts that automatically generate the geometry of your model. You can also generate the XML files. So a lot of the functionality that you see in the graphical interface, I've written Jython wrapper packages that allow you to make function calls and essentially do anything that you would do by pushing on the various buttons you can do through scripting commands in Jython, which would make life a lot easier, I think, in setting up more complicated models where maybe the interactive part would just be to do a little fine-tuning at the end. So anyway, there's custom classes that we implemented for that purpose, leveraging Jython. So this basically allows you both to set up your models, and you also can create custom GUI windows for additional interactive components if you wanted to, again, make things portable for someone else to use, as well as setting up post-processing scripts for visualizing data after you're done if you want to do it within this Java paradigm. Okay, so let's see. So I already talked about these two regimes quite a bit this morning, so I've gone through it kind of quickly here. I'll just mention that for the inertial regime, we've set up a kind of Verzlay-style integrator, and the way that the time stepping works is basically to do a half time step for the microstructure velocity. We update the particle positions, and then we do a half step for the fluid velocity, and then there's a slight lag that we've used in the calculations of the drag in the stochastic terms. So Verzlay is typically done for systems which conserve energy. This is in a dissipative system, so there's a little bit of thought that had to go into how to manage the stochastic forces in the drag terms in a way that gave good results. So I won't say too much about it, but here's just the way that we drive the system thermally. We then update the microstructure, the remaining half step, to get our n+1s and our hydrodynamics, and repeat this loop. So this is basically what's going on for the inertial Selm regime. And then we use a variant of Euler-Maruyama for updating the non-inertial overdynamics. There is an important issue of how to deal with this stochastic drift term. Currently, we've found that the stochastic drift term is fairly small, but you can also sample gradients, basically, of the stochastic drift on average to achieve that term if needed. And I could send you to our recent preprint where there's a predictor corrector method very similar to what Alex Donov and Eric Van Dyden use in some of their techniques to integrate stochastic dynamics. Okay, so I mentioned this idea of the adjoint conditions. I won't go through that in more detail other than to say that we have the ability to do immersed boundary style coupling as well as these generalized Faxon coupling. And the way we do it is through a table, a coupling table that you would load in the interface. So I just wanted to point out this aspect of the coupling operator so that when I show you in the interface how to set things up, it kind of makes sense what this coupling operator class and term is doing. Okay, and we already talked about this morning, the ability to do translational rotational mechanics. Okay, now what I didn't say much about this morning, but is in the current codes, which would be of interest to you, is oftentimes one way that these materials are characterized is to look at their rheological properties. In particular, looking at in something like a rheometer, you would apply a torque and look at the corresponding angular velocity of your probe, or the other way around. You might have a mode where you impose a constant velocity and look at the feedback. But at any rate, what you're measuring effectively is the shear stress in the material. You can also, I guess, measure the normal stress as well by looking at the other component in your device. So you're measuring the stress response of the material to an applied shear. And so in molecular dynamics, this has been sort of modeled by what's known as the less-Edward boundary condition. So rather than doing an affine transformation of your entire lattice or network, which would kind of impose the corresponding response, you can look at this as kind of like a sliding bricks model. So you have this centralized brick. The periodic images, instead of being in the normal location, are shifted slightly. And these can run in the opposite direction on the top and the bottom. And effectively, because you see a shifted periodic image, it's as if the material is being sheared, at least near the boundaries locally. And then internal interactions within the domain then set up the response. It turns out you can look at this equivalently as using a periodic box, but where the unit cell now has a shear to it. And so from that, what you can do is then look at the stress response. Now, it's an interesting question of what the effective continuum stress is, given that you have this molecular description. But if you think about stress, stress is essentially the amount of force material A is exacting on material B across a certain plane per unit area. And so you can use that concept of stress, although in the microscopic context, you don't want it to be sensitive to the location of your stress plane. So you average over all the different stress planes, and you can get various types of estimators, or so-called Irving Kirkwood stress formulas. So this is just showing how from the microscopic forces, if I know the difference between the two locations of, let's say, these pieces of this polymer that are acting on one another, that's going to contribute to the average given the displacement in that particular direction as I go through my averaging procedure. So I can weight the forces in this manner and back out an effective macroscopic stress from my microscopic forces. And so that we have that capability within the codes. And so what's interesting is to look at these fluctuating hydrodynamics adapted to this case when you have sheared boundaries, namely the less-Edward boundary conditions. And as I mentioned, in molecular dynamics, it's pretty straightforward. You just look at a shifted image and you add a velocity, right, across the boundary if you're looking at an image that crosses the top or the bottom. In fluid mechanics, it's a little more complicated because you have a continuum description, and you don't want to have these jump boundary conditions, because if you do that, that causes trouble with respect to doing fast Fourier transforms. If you also look at the periodic lattice, the shifting of the periodic images also breaks that translational symmetry. And so what we do instead is look at this deforming domain, and we basically discretize in time on a moving mesh. And so that creates a couple of problems, because now there are numerical artifacts that will disrupt that fluctuation dissipation balance that I referred to this morning. And so we've proven a little lemma that allows us to show that there's a way to choose the stochastic forces H therm consistently with a sort of moving or a time-dependent dissipative operator and still achieve the right equilibrium covariance. And so this is a formulation of that done now in this moving reference plane. And so the jump periodic boundary conditions then come in as source terms in the PD, and then that allows us to preserve the periodic boundary conditions and use, again, fast Fourier transforms. So anyway, these are some of the gory details. I guess I don't really think there's much point in getting too much into it. I could talk about this offline if it's of interest to you. Or you can look at our paper on this topic. Okay, so I thought what I'd do is go through a quick example. I'll motivate it here, and then we can go through and I'll show you how to set up the software to do this example of a Fini dimer. I mean, obviously you can do much more sophisticated things with these fluctuating hydrodynamic approaches, but I thought this would be a nice entry point. And this is kind of like the textbook example of a viscoelastic system where you have interesting rheological response. Okay, so the Fini dimer, the Fini stands for finitely extensible nonlinear elastic spring. And so the idea is that, you know, if you chose a harmonic spring, basically for some of these problems, you end up with issues with the bonds being stretched too greatly given the weakness of the harmonic force. It's not enough to restore the string if you strongly shear the system. If you do something like this Fini bond, what happens is that we use a logarithm of the displacement Q over Q naught, and you can see what's going to happen here. As I approach the extension Q naught, this potential is going to diverge. And so in some sense, the spring is going to get stiffer and stiffer as I approach that critical extension. So there's no way with finite energy to extend this spring beyond that finite difference Q naught. And so it's just shown here in the energy. I've chosen it to be 200 units. You could think of it as, I guess, 200 nanometers. And this is done, I don't know, K on the order of a couple kBt. Okay, so if you make a fluid full of these Fini dimers and you shear using the less-Edwards boundary conditions I mentioned before, the shear stresses in the fluid will tend to extend the dimer until it, of course, becomes stiff enough when it cannot extend any longer, and it will then tend to rotate. And so you get a coupling between the X and the Y, or X and the Z extension due to the nonlinear nature of the spring. If you used a harmonic spring, you would not get that behavior. If you now look at the setup of the dimers, you can look at what happens, and I'm just giving you the qualitative picture, if you were to apply different shear rates. So if you have a very small shear, these will tend to, by thermal fluctuations, be kicked around and take on random orientation. But as you increase the shear, right, these tend to basically get rotated to line up with the shear plane, right, in order to minimize the energy because of that, that extension no longer being possible beyond Q naught. So the thermal fluctuations every now and then will kick these out of alignment. They will get stretched, rotate back. And so if you go through, you can look at what the effective shear viscosity is of this model polymeric fluid as a function of the shear rate. And so there's a phenomenon known as shear thinning, for which the Finite-Dimer model is the classical kind of textbook example. Okay, so let me discuss this particular example and the modeling software. So I think most of you now have downloaded the package. You go to our website, mangoselm.org, download the latest release, and I have this tutorial in there. I think everybody's downloaded the software at this stage as I fiddle around with the display. Yeah, okay.
Yeah.
Okay, so let me go through the steps of setting this up. So I realize I have two computers here, so this will be interesting. I'll run through the steps, and then I'll switch to the other computer and kind of go through them. So if you go to the MangoSelm interface, you'll notice the pointer doesn't really register on this screen, but you'll notice in the upper left corner, there's a file folder picture. And so if you go to there, or you just choose in the file menu, open, if you go into the, I should update the name here. If you go into the directory under, let me open it on the other computer so you can see it all. You'll go under the source directory, user selm, examples, and it will be Finite-Dimer. Let me load up things on the other computer so you can see it. Never done one of these live demos before, so this will be interesting. So what you do is you, I have a pre-configured project, although you're certainly welcome to set up a project from scratch, but just in the interest of time, just to kind of get you going on something. So if we go to, let's see here. You go to my downloads directory. Oops. Oh, this was the interesting issue with the display we had. Okay, so I'll go to downloads, MangoSelm there, the source directory here, user selm, there are a bunch of examples here in Mango projects. And if you go into Finite-Dimer and you pick the Selm Builder project file and click open, then magic happens. Okay. So this is loaded up the Finite-Dimer into the display. And so here's the picture of the Finite-Dimer showing you the geometry. And then there's a bunch of menus here, and I'll walk you through these menus. Everything is, of course, automatically been set up for a viable simulation for you, given the fact that I made this prepackaged project, but normally you'd have to do this yourself. So this main basically sets up the naming conventions for things. You can add descriptions, random seeds. And then, as I mentioned, there are these four basic components: the integrator, the Eulerian, Lagrangian, and the coupling operators. And that's all here that have been set up for you. And this is kind of summarizing for you the overall structure of the model. Then what you can do to set up the Lagrangian interactions is you would go here to set up what your Lagrangian degrees of freedom are going to be. That's what DOF stands for. So you would have, add, LAMMPS, atom, angle, style. You would click that, and then that would create one of these lines. In fact, I'll just make one here. So you see that, and then you put your name of whatever that particular structure is. I'll just remove that here. So we call this particles. And then that's going to come up later when I start doing coupling operators to decide what couples with what, right? The next tab specifies the properties of the Eulerian mesh. And so what's done here is you have the name that you're going to give the mesh. There's a particular type that's a string that's going to be read to determine whether it's a uniform mesh or whether you're doing finite elements or something else. Then there's some parameters, of course, for this particular mesh type. In this case, the delta x in the mesh. This is going to be just a uniform discretization mesh that you would use in finite differences. And this is showing the number of mesh points in each direction, where the mesh is centered. And then some other attributes which are related to display and output. So do I want to output this to be VDK format, and the fluid velocity field, the pressure field? Do I want to look at the force density? Oftentimes that's useful in diagnosing what's going on in your model. So here I have it checked to do the fluid velocity and the force. Okay, then what you would do now that you have your Lagrangian structures and your Eulerian mesh, and you could have multiple ones in principle, is now you can create a coupling operator. And for now I just have one type of coupling operator that's useful for that uniform periodic mesh, so I've created that here. and just called it coupling op. Okay, then there are also interactions that you can set up, and that's done in this manner. So there's different things you could do in LAMMPS, like you could have pair interactions, you can have bonds, you can have bond angles, you can have special bonds. You can even have custom interactions. And if you do custom, then there's a parameter named field that you can set. And the main point in this is this will allow you to define the topology of how these interactions behave. Then there's the integrator, and the parameters are given here, the time step, and other information relevant to the simulation, such as the shearing rate, which is given down here, along with the direction of shear and how often you want to save the data. And then a few, just to give you kind of a tour, there's a few little preferences here for how things are displayed. And we also have some stuff related to the tables, which I've turned off, that can show you the physical units, and you can come up with a little display for how you want numbers to what precision. Okay, so there's a couple customized things. Now, the way that you actually edit these things in practice is you go down here to this lower left tab, and you can select either the interaction editor, the Lagrangian editor, or the coupling editor. So if you go into Lagrangian editor, this is basically what allows you to deal with your topology of whatever structure you've set up. So you can do things like moving points around. So if I take this point and select it, I can move it. You could add points. You could add additional Feeney dimers, which I'll do in a moment. Not in this demo, but in the later one if there's time. You can obviously remove points. You can also edit things directly in this spreadsheet fashion. And the display is a little bit complicated, but here we go. And so what I've done here is if you click on the point locations, now you have all the values there, which you can edit easily by hand. Or you could also do that through the Jython interface through the script commands. Okay, so this is all of the standard things that you normally need to set up in LAMMPS, but it's giving you a graphical interface to that. Similarly, you can set up the interaction editor. This is for setting up the bonds, and I'll show you an example, not right now, but in the future demo, maybe one or two, how you can add and remove bonds between your particles by using the graphical interface. And the important thing here is that in order to add a bond, you have to push Control while you're selecting the first and the second bond. So that's important. So look at the README files in the package. I explain those types of things. And then last but not least, we have the coupling operator. This kind of tells what talks to what. And so here we have the, you can choose a particular Lagrangian type, in that case particles. You choose a particular Eulerian type, in this case the uniform mesh. You would click Add, and then up here you would have a list of that particular coupling operator. This is now showing you down in the editor the properties of coupling op, that particular one. And so this is just giving you the type of coupling. This is maybe the important one. You have the type of coupling, in this case being T-kernel 1, which is just immersed boundary style coupling done from a table. And this is really important. You have to set up the location of the weight table. See, weight table file name. And I've noticed that depending on your configuration, this sometimes can be confused. And so you should go into Downloads, Mangelselm 2.01, Source, User Selm, Examples. And then if you go to Common, there's a table there sitting for you. And you could obviously come up with your own kernels that you use. In this case, I've done a version of like a Peskin Delta style kernel. So you select that. It's important just so that it registers in Java to select another field. And so now that's all set up and ready to go. Okay, now to generate your model, if you're happy with the topology and how things are laid out, what you can do now is go up here to the gear. And if you click on the little gear, it's probably coming up on my window here, but let me move it back. Then this generate parameter files comes up. And so what you can do here is choose a path for your script and XML files, which will automatically be generated. I choose to include the comments, but if you're interested in keeping the files parsimonious, you can, of course, turn that off. Okay, so now if you click on the ... that pulls up a file window. And this is where it's going to generate the actual data script files. So what I like to do is go back into the examples directory where I had my projects, and I create, for example, Feeney, Dimer, and then I like to say something like done or completed just to keep things nice and clean. And so I'll just put it in here. Select that as the path of where I'm going to generate all my XML files. Push generate, and then down here it displays in the output window that it generated all the files with no known errors. Okay. So now if I open up my my Linux window here, prompt, then I can now look at this directory, and I'm just going to show you what files were generated if everything went as planned. Okay, so here are the files that were generated by the Mango SELM interface. So you have the coupling operators, and you're welcome to open them up. They're all text files, standard XML format. And so if I open them, for example, here, you'll see this is the XML file specifying all that coupling operator data that I had set up. Then I have, the Fini dimer set up well. But what's really useful is I've also had the scripts set up for LAMMPS. So LAMMPS now has the read data that it needs in order to set up the read data that it needs in order to set up the geometry of the dimer, which in this case is just 2 atoms with 1 bond. And you see I've set up the domain size based on the Eulerian information. And so what's useful here is it sets up LAMMPS consistently with what the SELM solver needs, right? Because you don't want to set the domain up for your read data to be one thing in LAMMPS, and then you have your solver 5 times bigger, right? Then the things will be mismatched. So this is the kind of entry point where I think using our graphical interface just to get comfortable with these things would be a good starting point. So this is just setting up the bonds for Fini and the bond topology. Okay, and then the driver script is given here. This is the LAMMPS script file. This is what really makes everything happen in LAMMPS. This is the thing you're ultimately going to call. And so this just sets up, a lot of the things that might be a bit challenging at first to get consistent with the SELM package is now automatically generated for you. So it sends up the atom style and the bond styles and what kind of boundary conditions you have, how to modify the sorting of neighbors to deal with periodic images. And then here's the key line that would allow you to adapt your own models to using our codes, which is our integrator is basically a fix in the nomenclature of LAMMPS. I don't know why they call them fixes, but anyway, that's the choice that they made, and so we follow that convention. So by using this script command fix, you give it a name, which we call it 1. It's going to apply to all the atoms, and then this is the SELM integrator to be used. And then you say you just pass one thing to our SELM integrator, namely this file name .selm params. And now an XML file tells everything to my SELM code where to look for all the other XML files for Lagrangian or Lagrangian structures, the Eulerian structures, the coupling operators, the other integration variables. Okay, so this is kind of the master XML file, if you like, which drives all the other XML files to get processed correctly. Okay, so it took a while to figure out a good architecture, software architecture to do that, and so it looks a little technical at first, but there's a logic to it because it allows you then to extend things very easily without having to change codes upstream. You can just add a new Lagrangian type or a new Eulerian type, and it all fits within seamlessly. Okay, and then there's some other little commands here to dump basically the data to a DCD file with some frequency, and there's a couple little things that you can play around with there if you like. And number of time steps and the time step to be used. Okay, and all of this has been kind of grabbed from these different parts of the model setup and made into now a consistent LAMMPS script with the SELM integrator backends. Okay, so some of these values, I've tried to reduce repeats of the values in the LAMMPS script and in XML. So whenever I can, I try to get it from the LAMMPS script when the integrator is working. But there's some things which are inevitables, like the Eulerian mesh sizing and so on. Okay, so let's give this a try, see if we can run the simulation. It's always exciting to do these things live because you never know what will happen, if things will go as planned. But at any rate, if you look in the bin directory, which is quite a ways down here, I noticed, I've, for at least for a x86 architecture, and this was done for Ubuntu, I'm sure it will run on other machines as well. This is the main compiled binaries and LAMMPS that will run everything. So I'll just symbolically link it using, well, call it run. Okay. So now in the current directory, I have this, I have the run script set up. And now what I can do is to run that particular script, you would say run, which is just LAMMPS, in Fini dimer, and then you feed it the the LAMMPS script. Right? And so if I press enter, then now that runs and sets up the simulation of my Feeney dimer running in LAMMPS with those specified time steps. And the output, I just open a new window here. That's given by this DCD file. Let's do it here so you can see the length of it, right? And you'll see that that's growing, so that's running nicely. Okay, so let's say we want to visualize this. If you go just down one directory, I set up a nice little visualization script for VMD that automatically generates a good visualization for this Feeney dimer. And so this will just load in the current progress of that DCD file and provide you a graphical representation of the model. Okay, it's going to take me a little bit just to transfer the windows here so you can see everything, which because of our display challenges. Okay, so this is showing the model, and let me get the other component on the screen as well here. Okay, so let's see, kind of limited real estate, but there we go. Okay. So you can play around with that a little bit to get it to display nicely. So there's our little Feeney dimer, and if I bring it back to the beginning, you now can see it diffuse around with the fluctuating hydrodynamics integrator. Okay, and then now that you have the DCD file, you could do post-processing in order to do further calculations. You could set up, of course, simulations with additional Feeney dimers. I'll just let you play around with the interface and just kind of switch back to my other computer just to kind of show you the outcome of a few other examples and tutorials which I've included in there. And I don't think with the amount of time we have, we can go through that. But I can at least show you what the outcome would be, and you could do this on your own. Okay, any questions about the setup for the Feeney dimer? Because if you can do the Feeney dimer, then you pretty much can do all the other models that I've put in the tutorials. As well as, once you understand that structure, you could easily set up other types of simulations of pretty much anything that you can model with a force law and LAMMPS. And so it's just showing the Feeney dimer diffusing over time. So if you let it run longer, you do have to be a little careful about the wrapping of coordinates and so on, and specifying the bonds carefully so it displays correctly in VMD. So now this is showing if I were to do a large ensemble of Feeney dimers, and in fact I did set up one of the demos. If you go to Feeney Fluid, this is still a little bit too dilute to really do the analysis that I'll show you in a minute, but just to give you a sense of it, right? These are now a bunch of Feeney dimers, which I set up in hand. I just point click to add the bonds, right? You can arrange them however you want. You can go whatever concentration you want. Take you 5 minutes, right? So now what I did is I simulated that using the, there we go. So now you have a large number of them, and now they've been sheared. In this case, the thermal fluctuations are rather small, just to kind of show you how if you have small temperature, or if you have very large shear, things will tend to line up almost perfectly with the shear point. But anyway, you can get an idea of how the Les-Edwards boundary conditions are operating, right? So those are moving much faster than the unit periodic box because of that sliding bricks model. And so the only ones that are really being computationally tracked are within the drawn region, right? All the other ones are just periodic images with the sliding bricks model taken into account. So it's mimicking, right, a sheared material where that center cell.
What's the interaction between?
What's that? Oh, those are the Feeney dimer interactions, just two. And then hydrodynamics through the fluctuating solvent.
The different particles, not the
two particles. I some of them I think I put like a Leonard-Jones law so the beads don't overlap. Yeah. And so if you look in the Feeney potential, it's got Leonard-Jones built into it. Mm-hmm. That kind of keeps it just from collapsing to a point. So now if you look at, you can look at using that stress estimator that I showed you in the previous slide, you can look at the contribution to the shear viscosity. So this would just be reading off the shear component, the velocity component over the shear rate. And what you notice, quite interestingly, is you get deviation from the Newtonian response, right? The Newtonian response, the faster you shear, in proportion, the more shear stress you have, right? So notice I'm normalizing by the shear rate. So if this were level, that would be a Newtonian fluid. What we see here is as you, if you shear at a fairly slow rate, and this, like let's say this medium case, the thermal fluctuations kick you out of the shear plane, you stretch, you come back. And so that's going to lead to forces being transmitted laterally. And so you have a finite contribution to the shear viscosity. Of course, as you increase the shear rate, you're going to get more and more alignment with the direction of the shear. The thermal fluctuations are going to play less and less of a role, right? The shear suppresses the thermal fluctuations, kicking you out of the shear plane. And so you get the so-called shear thinning behavior, and eventually these things will all be perfectly aligned with a negligible perturbation, and you'll essentially have, negligible contribution to the shear viscosity. So that's known as shear thinning, because the more rapidly you shear the fluid, in some sense, the less viscous it responds, which is maybe similar to the type of response you would have expected if you had less concentration, right, of your polymer. Okay, and then you can also look at the normal stresses, which are just the other two components of the stress tensor. And so I'll just summarize some of the other demos if you're interested. For fun last night when I was putting these together, I was using the graphical interface to make a polymer knot. And so one of the features I'll mention of the immersed boundary method, which is very nice, is because everything is in the dynamics is referenced to this common underlying velocity field. Basically, the update is a homeomorphism. If this were a continuous curve, obviously this is not a continuous curve. And so what that means, if you had a continuous curve, that the dynamics of the immersed boundary method would preserve your topology, right? You would have a homeomorphism driving, the initial configuration to the later configurations. Here it's a finite bead model that I set up, but nonetheless you can see through those correlations that it still maintains the trefoil knot topology. So I thought that was kind of cute. And so I included that as one of the examples. Of course, if you run it long enough, it will probably unknot, because I didn't have a large number of beads or even sterics put in for the bead-bead interactions. But if you had a chain with a lot of little beads on it, then it should maintain its knotted structure. And then this is just showing a little polymer here. Simulated again, I set up the geometry with the Mango interface. And you could do, star polymers. You could do all kinds of interesting topologies. You could take a icosahedron and refine that, and you could do polymerized vesicles. So you can do a very wide range of mechanics problems very easily using this software, incorporating fluctuating hydrodynamic effects. Basically, anything that you can set up in LAMMPS with a particular force law, you can run through our codes and simulate. And just as a sort of motivation, I'll mention some of the more sophisticated models that we've been working on, and I realize getting close to lunchtime, always dangerous. So I'll just mention very quick just a few movies about this implicit solving coarse grain model that I was talking about in the talks this morning. And so I'll just show you a few little results, kind of showing you where you can go with these things. So this is just showing these little 3-bead models which model the amphiphilics, which now self-assemble, but of course you can't see it because it let's see here. All right, here we go. So I put a vat of these together, much higher concentration than what you saw in the Fini example, and it's running beautifully on my laptop. But just don't worry, I'm not going to spend too much time on this. I'm mainly just going to show a few movies just to kind of give you a sense of the things that you could do with the techniques. And we could talk more offline about this particular problem and others if it's of interest to you. So I just want to show you that you can self-assemble these interesting structures. If you take these amphiphilic molecules, this model is due to Marcus DiCerno, and we've extended it to include kinetics through this fluctuating hydrodynamics thermostatic. And so it forms these little disks because that sort of minimizes the line tension because the tails don't want to be in contact with the water. There's an attraction between them, but anyway, you get an effective line tension. And there's also kind of a bending elasticity. And if you look in the upper right corner, once it gets to a critical size, the line tension kind of wins over the bending energy. In other words, you're big enough so that you can curve around without too much of a penalty, and you form a closed vesicle. And so one of the things that we've been looking at is using vesicles made of this self-assembled bilayer as a way of probing mechanical properties of this kinetic implicit solvent coarse grain model. So looking at things like what's the effective shear viscosity of such a bilayer, or what's the effective intermonolayer slip as I change different parameters at the molecular level. And that's, I think, a useful first step in trying to build more sophisticated biophysical models that are sort of well connected with the continuum mechanics. And Ben Gross is here, has been doing a lot of work on the continuum solvers to relate to these models. And I won't go into a lot of this stuff. So there's a exterior calculus framework that we are developing, a computational method that can compute these various exterior operators to compute hydrodynamic fields on interesting manifolds beyond just doing the spherical case. And so anyway, by looking at correlations in this coarse-grained model and relating that to hydrodynamic fields in the continuum mechanics, we can use linear response theory to back out things like viscosity and intermodular slip, which we're working on. I'll just make one other remark. We've also, I mentioned, made this finite element solver for doing fluctuating hydrodynamics. So this is showing a case where we have particles diffusing through a device that has a bunch of posts in it. And ideally we would do polymers. We just did particles as our initial run, just to keep things simple. So this is just showing the finite element formulation of the fluctuating hydrodynamics, and it's just passively diffusing, and you see as things get a little closer to the posts, they kind of slow down as they should because there's a sort of position-dependent mobility. And we've done cases where they're passive or when there's an active flow through the posts, and my student made this like dramatic-looking movie that he was very proud of, so thought I would show that since that's fun. And so this is just showing now with that drift, the hydrodynamic fields I showed. Now if you start off them in one location, unfortunately the contrast on the screen isn't showing it, but there are little posts and it's diffusing around those posts, partly following the streamlines, but then the Brownian motion, of course, causes you to switch streamlines. So as you approach some of these stationary points, you kind of branch left or right based on the particular Brownian motion that's occurred up to that time point. So anyway, that can have interesting consequences for the transport of different types of colloids and polymers through such a device. But this is very much a toy model. This is more just to kind of get the solvers and the computational techniques in place. And if you're interested in talking more about applications of this finite element formulation, I'd be very happy to talk with you as well. And this is just showing a little calculation that, again, kind of illustrates the hydrodynamic feature and the role of geometry. So this is just showing as I go across the post here, if I were to look at the mobility of one of these particles, the Brownian motion, if you like, or the active force response, you would see artifacts from the fact that you have these no-slip boundaries, confinement or interactions with these no-slip boundaries in your proximity, right? Wall effects. And so it's just showing that when I'm far away, or when I'm near the channel wall, I have a drop in mobility. And then I go up, right? And then as I approach one of the posts, right, my mobility drops down, and then I go up again. So we're capturing potentially interesting kinetic effects that, again, would affect mixing and other types of phenomena involving hydrodynamics and Brownian motion and such complicated geometries. But again, this is all toy models just to kind of show the proof of concept. Okay, so I think maybe I'll summarize there. I think we have some interesting computational capabilities that have come out of this work with the CM4 over the years, developing new solvers for doing fluctuating hydrodynamics in a range of different physical regimes, ranging from inertial all the way down to these kind of overdamped techniques where you don't need Green's functions and you can solve within confined and interesting geometries using finite elements with Brownian motion hydrodynamics incorporated consistently. And we've also developed this software package that both allows you to run simulations in LAMMPS as well as this graphical user interface that allows you to set up models quite interactively and hopefully is an easy entry point for you or your students to make use of these new tools that we've developed. I'll just want to acknowledge a few people. So Ben Gross is actually here. He's working on the differential geometry solvers that I mentioned. We're basically going to take a lot of this stuff and start doing fluctuating hydrodynamics on manifolds. So where you have curved interfaces. So he's been doing a lot of nice mathematical and computational work on that. John Sigerson did a very nice work on a lot of the coarse grain simulations. Yahong Wang did work on the slit channel geometry. Pat Plunkett on the stochastic finite elements. Gil Tabak helped me with the stochastic reduction methods. Ming Gong is here. He's working on parallel implementation for the stochastic finite element techniques integrated with the Sandia package Trilinos. And then Inabir Sidhu has been working with me on doing electrokinetics in these channels. Very, very nice working with all of them. And I'll also mention some of the CM4 collaborators. Chris Seifert, Jonathan Hu, and Mark Parks have been very helpful with the Trilinos integration and being involved with the finite element formulations for fluctuating hydrodynamics. Emily Freshnick, we've been talking a lot about these coarse grain models for looking at electrokinetics. And then Juan Lee and Greg Schenter and Nathan Baker, we've been talking a bit about different interfacial problems related to some of this work that I taught. And Matt Trask has some very nice work that he's done on moving least squares, and we're also trying to discuss ways of taking some of these fluctuating hydrodynamic approaches and basically using a lot of the mathematics we've developed to do finite elements and finite difference type methods, but move into other realms like moving least squares or smooth particle hydrodynamics and contribute there. So. All right, so thank you all for your attention. This is a lot of fun. I'm looking forward to the rest of the workshop and hearing about other people's software and solvers. You can go to our website for more information or just contact me. I'd be really happy to talk with people who want to use the software on interesting applications, or if you're interested in making extensions. Definitely reach out to me. I'd be happy to help you, use the software well for your purposes. So. All right, so it's been a lot of fun. So thank you again for your attention. Yeah.